let's talk about arithmetic series. If you know the series is arithmetic, that is the key. We know that this is an arithmetic series. You can actually use this equation to solve for the sum. So let me give you this example right here in example 3. I'm going from 1 to 12 of this equation. All I need to know is n, the first term, and the last term, and I can very quickly add up all the terms together. So let's see, I know n is 12. I'm going from 1 to 12. That's 12 terms that I'm adding together. I just need to find my first term by plugging in 1 into my equation, which is -1. And I need to know my last term by plugging in 12 into the equation, which is 43. And then I can plug them into this formula. And note, this formula is on your reference sheet. You just need to know how to use it. This is how we find the sum of an arithmetic series. This is an arithmetic sum. So I have 12 over 2 and my first term plus my last term, which is 6 times 42, which is 252. So if I were to write all these numbers out and add them together, this is the answer I would get. And it's a really fun, awesome, fast equation to do this way quicker than just finding them all by hand and adding them together. Now, before we go on to our other problems, I do want to talk about this equation a little bit because it has a really fun math story behind it. This equation was actually created by an 8-year-old boy. His name was Gauss, and he was in school, 8-year-old math class, and he was goofing off, and the teacher was sick of him. And she was ready to kick him out. Or he, I don't know, whoever the teacher was ready to kick him out of class because they were so sick of how much he was goofing off. And so they said, Gauss, you need to solve this problem. Thinking, if I give him a really hard problem, it's going to keep him busy for a while, and then he'll at least stay out of my hair for a little bit. And Gauss's teacher said, I need you to sum all the numbers from 1 to 100. Oops, I'm running out of room here. Let me give myself a little more room. $98, $99, $100. Thinking that adding all these numbers up might take Gauss several hours. It might keep him busy, keep him out of the teacher's hair for a while. However, 30 seconds to a minute later, Gauss comes to the teacher with the right answer. An 8-year-old kid. How cool is that? And the teacher was like, Gauss, how did you do that? There's no way you added up all those numbers that fast. And here's what Gauss noticed. Gauss noticed that if I take the first number and the last number and add them together, I get 101. If I move inward, take the first number and the last number, add them together, I get 101. Same thing, if you move inward, 3 plus 98, 101. 4 plus 97, 101. And it gives you the same answer. And if you keep doing that moving inward, you're going to have enough pairs of numbers equal to half of the numbers you started with. So I was going from 1 to 100, but since they're in pairs, I'm going to have 50 pairs of them, half of that. And it's 50 times the first number plus the last number. So 50 times 1 plus 100 gave me 50 pairs of 101. He just multiplied that together real quick on his paper in his head and got the final answer. Gauss was a pretty smart 8-year-old. Needless to say, the teacher did give him a little more respect after that because as an 8-year-old, he came up with this formula that we still use today. So that is where this formula comes from. This is why it works. I think it's a really fun one to talk about. So let's move on to our next example and let's start to apply this formula in different ways. So here we have the first term of an arithmetic sequence is 15. First term is 15. And the 10th term is negative 12. We want to find the sum of its first 10 terms. We also then want to find the sum of its first 20 terms. So let's remember our equation, Gauss's equation. N over 2, half of our pairs, and the first one plus the last one. So let's do this one first. Let's split this in half. We'll do the first 10 terms here, and then we'll do the first 20 terms here. So if I want to do the first 10 terms, that means n is 10, and my first term is 15, and my last term, the 10th term, I know is negative 12. So I can just plug all those into Gauss's equation. And 10 divided by 2, first one plus last one, that gives me 5 times negative 3, which is negative 15. So if I take the first 10 terms and add them all together, this is what I'm going to get. Now I want to do the first 20 terms. So now n is 20. My first term is still 15, but I do need to figure out what my 20th term is going to be. So to do that, let's come up with our explicit formula and then plug 20 into this. So if this is my explicit formula, let's see. So I know this is arithmetic, which is the first one plus dn minus 1. There's my arithmetic explicit. I know my first term is 15. I don't know what d is. However, I do know my 10th term, plug 10 in for n, is negative 12. So I can use that to solve for d. So let's see, this is 15 plus 9d minus 15. So 9d equals negative 27. D is negative 3. So I'm minusing 3 every single time. So that tells me my explicit formula is 15, my first term, minus 3, and minus 1. There's my explicit formula. Now I need to find my 20th term. So plug in 20. And if I solve all of that, I'm going to get that my 20th term is negative 42. So now I know what my n is. I know my first term. I know my last term is negative 42. I can plug all that into Gauss's equation. I have half as many pairs. First one plus the last one. Calculate all that. I get negative 270. So there's the sum of my first 10 terms and my first 20 terms. Let's try example 5. The first term of an arithmetic sequence is negative 12. Its common difference is 5. And we want to know how many terms of this sequence must we add together to get a sum of 345. So we need to figure out how many n's do we need. So let's plug in what we know into our explicit formula. So our explicit formula is the first term plus our common difference, n minus 1. I'm going to, common difference is 5. Simplify this for us, which is 5n minus 17. So there's my explicit formula. Now, I want to do the sum of the first term to the last term. I don't know what the last term is to get 345. Now, since we are summing an arithmetic sequence, we know this is still Gauss's formula, because we're summing an arithmetic sequence. However, this time, I don't know what n is. I don't know how many terms I have. I do still know the first term is negative 12. I don't know what the last term is, but I do have an equation for it. 5n minus 17. I know that's my last term is whatever n is. And this all has to sum up to 345. So here's what I would like you to do. Pause the video at this point and try to solve this equation. You are going to get a quadratic that you will have to factor, and it's not a nice factoring. I'll warn you that right now. So it might take you a second to factor it. When you factor it, you're going to get a negative answer and a positive answer. However, since this is term numbers of a sequence, you can't have the negative fifth term of a sequence. So whatever your positive answer is from your factoring of your quadratic is your final answer. So pause the video. Let's review our factoring and skills here, and then come back to check to see how you did. Like I said, this is a brutal factoring. So I simplified everything out. I got this. I times everything by 2 so I wouldn't have fractions. That gave me this equation, brought the 690 to the other side so that I could factor it. 5 times negative 690 is negative 3450. So I need to multiply to negative 3450 and add to negative 29. Took me a little while to find this is the pair of numbers that does it. So I split my negative 29 up into those two. Find what those two have in common, find what those two have in common, factor it out, and there's my factored form. So then I set both of them equal to 0 to get negative 9.2 and 15. Can't have a decimal of a term, and you can't have a negative of a term, so that one doesn't work. So this is 15 terms. So how many terms of this sequence do I need to add together to get 345? I need to add 15 terms together to get this answer. Last arithmetic series problem, and then we'll move on to geometric series in the next video. This is a story problem. We have Margaret, who has had a minor surgery. On the Sunday after her minor surgery, she is able to walk a half a mile. So this is n, a sub n, and n is going to be each week that she walks. So on her first Sunday, she walks a half a mile. Each Sunday, she walks an additional quarter mile. So on the next Sunday, she walks the half a mile and an additional quarter. On the next Sunday, she walks what she did last week and an additional quarter. And the next Sunday, we continue the pattern. Walks what she did the previous week and an additional quarter. And she does that up to 8 weeks. And it says, after 8 weeks, what will be the total number of miles she has walked? So the first thing I would do here is come up with our sequence. So this is 1/2, then I get 3/4, then I get 1, then I get 1 3/4, 1.25. Let's change these to decimals. So for my explicit formula, it looks like my first term is 1/2 my 0.5, and I am growing by adding a fourth each time. So there's my explicit formula. And while we're at it, let's simplify it. So I get 1/4 n plus 1/2 minus 1/4 is 1/4. There's my explicit formula. Now, we're adding all of these together because I want to get the total number of miles that she has walked. So to get my total number of miles, that's Gauss's formula, because we're summing all of them together. I know I'm adding the first 8 terms. I know my first term is 1/2. That's how long she walked her first Sunday. So I just need to figure out how long she walked on her last Sunday. So that would be a sub 8. Plugging 8 into this formula. 1/4 times 8 plus 1/4 gives me 2.25. So on her last Sunday, she walked 2.25 miles. Plug that into my calculator, and I get that by her 8th Sunday, she has walked a total of 11 miles. So those are some fun application problems for arithmetic series. In the next video, we'll jump into geometric series, which is a very different kind of equation, a very different kind of thing than we've dealt with thus far.